Hello friends, it is Ben again. This is a video for the differential calculus class. We are taking a look at some problems where we're going to look at the idea of inverse functions, and we're also going to look at the ideas of solving logarithmic and exponential equations. I'm trying to keep this sort of thing fairly short because if I don't, I will just go on and on with super long videos that, are more than you want to actually sit through. So the thing I want to do here is to go ahead and share my screen, and we'll see how things go. Okay. All right, looks like it's going to work. All right, so the first problem we're looking at here is looking at the notion of inverse functions. And what you got to know to do this is that two functions are inverses if when you compose the two functions, you get them to cancel out and you just get x out of it. Okay, so I constructed something real quick here for our example that ought to have that sort of cancellation property. But what you need to do is to actually show that that property happens. So when I want to say something here about f of g of x, then I need to go back and say for f of x, that meant to take the square root of the x plus 2. So I will, instead of x, put g of x and have that, with this note here that my g of x needs to be greater than or equal to -2. And then I'll go in and say, well, g of x really means x squared minus 2, but then I'll have to have a plus 2. And this part here about x squared minus 2 needs to be greater than or equal to 2. And do I need, I need to put a negative there, okay? And then that will simplify into the square root of x squared. And we need for our x squared to be greater than or equal to 0. But this really is the absolute value of x. If we take this part here and look at just the branch where x is greater than or equal to 0, then we have x out of it. Okay. If we don't do that, x greater than or equal to 0, we don't actually have that. So that is a little bit of a subtlety in this, that we really needed this assumption here in order to have this turn out to be inverses of each other. Now, we really ought to go ahead and check the other end of this as well, talk about g of f of x, and that would mean that you need to have f of x, the quantity squared minus 2, with your f of x being greater than or equal to 0. And that, of course, is going to mean that you've got a square root of x plus 2 squared minus 2. And I forgot to write down f of x rule. The square root of x plus 2 is greater than or equal to 0. This part here, the square root and the square are going to cancel, and you'll have just the x plus 2 minus 2. Now, the reason that you don't have to worry about any sort of absolute value stuff with that is that when you talk about a square root and you don't say plus or minus, then it's not plus or minus, it's just plus. when we talk about square roots, we were talking about the principal square roots. So this part here, we do turn out to get an x, but we ought to make note here that we needed to have our x's be greater than or equal to -2, because if we didn't, then we couldn't actually have evaluated that square root of x plus 2. So anyway, though, in both these cases, we've gotten x out as an answer. We do have some provisos on them, but that has to do with what's going on with your functions. All right, so that's a quick example showing that two functions are inverses of each other. A maybe more interesting kind of example is to get a function and be asked, what is the inverse of this? Now, I purposely chose an example in this case where it's a little bit of a pain in the posterior to actually show this. But here's your process. What you're going to do is to take your f of x and replace it with a y, okay? And then when you write things down, swap the role of y and x. That is what inverse functions do. They swap the roles of the x variable and the y variable. Then once you swap them, do the algebra in order to solve for the y, and that'll get you your inverse. So easier done than said here, all right? We will be thinking about y equals 2x minus 1 over x plus 2. The swap puts in x equals 2y minus 1 over y plus 2. Now, we're going to try to solve for y. Hypothetically, we might run up against sometimes where just the algebra is so hard that we can't actually get it done. But this one shouldn't be too bad. What you're going to need to do is to cross multiply, and we'll have x times y plus 2 equals 2y minus 1. So that means xy plus 2x equals 2y minus 1. We're trying to solve for y, so we're going to get all the y's on one side. And so we'll have xy minus 2y. We're just going to throw everything that's not a y over to the other side. We'll have minus 2x minus 1. Then over here on the left-hand side, since what we're trying to solve for is the y, we'll factor out the x minus 2. And then we can divide and say minus 2x minus 1 over x minus 2. That's what our inverse is. But you should write down that your inverse, is that there. Okay? So somewhere or another you need to kind of indicate which piece is your answer. Because if you don't come down and say what your final answer is, I mean, hell, we could have just right at this point here said, aha, implicitly that implies what my answer is, nanny, nanny, boo, boo, and we're done, right? So you need to come to some sort of a formality of your ending there. So, all right. Hope that works. Now we're going to take a look at logarithms and exponentials. And I need with this for you to understand that if I talk about the log base b of x, that is the inverse of talking about b to the x power, okay? So oftentimes, and you'll read a textbook that talks about something like this, and they'll make the point that this can be rewritten as saying that b to the y is equal to x there, okay? The main big thing for you to think about, though, is that logarithms and exponentials of the same base will undo each other. So in this question here, we're asked to solve for x in this equation that has something to do with log base 2. So what we're going to have to do is to, first of all, use our rules of logarithms. These two logarithms are being subtracted, and if two logarithms are being subtracted, you can pull them together as the logarithm in the same base of the division, like so. And that's supposed to be equal to 3 there. Now we use that idea about rewriting to either write x over x plus 1, the stuff inside, is equal to base to the power, or alternately, you could have written this as 2 to the log base 2 of x over x plus 1 is equal to 2 to the 3. Those would be exactly equivalent sort of things to do with each other. It's just that at this point, you'd have to say, aha, that turns into this because your logarithms cancel each other out. So either way you want to write it, totally fine to do there. Now we have to know that 2 to the 3 is equal to 8. So we can cross multiply again, have x equals 8 times x plus 1. So x is 8x plus 8, which means minus 7x is equal to 8, and x is equal to minus 8/7. Okay. Now, the difficulty with this is that now we have a negative value for x, and we're not actually supposed to stick negative values in to that logarithm up there. So technically speaking, we should say that this has no solution because x equals negative 8/7 cannot evaluate log base 2 of x. Okay, this is what's referred to as an extraneous solution, and it just had a problem that cropped up like that. So, all right. So let's go ahead and take a look at another problem here. And this one, we have e to the 2x minus e to the x equals 12. Now, I need you to note in this that I've purposely designed a problem that's going to have a little bit of difficulties in it, but it's also going to illustrate a couple of things at the same time. Okay, so the thing that I wanted to illustrate here is we have what's referred to as an equation in quadratic form. E to the x and e to the 2x, e to the 2x is really the square of e to the x. So if I rewrite this as e to the 2x minus e to the x minus 12, that is in effect a quadratic equation, but with the variable being this weird e to the x in it. Okay, so if you'd like to take an extra step there and write something like y squared minus y minus 12, you're totally fine with doing that. If you can do the problem without that, it just saves you a couple of seconds. Okay, I'm going to go ahead and do it like that because it makes it easier to see what's going on. I'm going to factor that into y minus 4 and y plus 3. And so that says that my y has got to be equal to 4, or my y has got to be equal to negative 3, right? And then substituting back in, you say, I've got e to the x equals 4, or I've got e to the x equals minus 3. If you've got e to the x equals 4, in fact, anytime you've got an exponential on one side and just a number on the other, you can take a log with that base on both sides. And because those two functions are inverses right there, they'll cancel out, and you have just x equals log 4, and you get a solution. The problem that we have over here on the other possibility is when you say e to the x needs to be equal to -3, if we looked at a graph of e to the x, we would see that the graph of it is always above the x-axis. That means that you can't have x equal to a negative, I'm sorry, you can't have e to the x equal to a negative number. Consequently, this is just an extraneous solution. Now, I will mention in passing with that if we were living in the world of complex numbers, it actually would have a solution. You can take an exponent, take a logarithm of a negative number if you're allowing your exponentials to have complex values in them. Not really something that we're going to try to do, just because the standard calculus, you end up not doing that. So it is totally a worthwhile thing to look at, but it's just not in the course of what we normally will look at. If you are interested in doing something in the direction of engineering, then after you finish the regular calculus course, you should look at a complex variables course and really get a better feel for that sort of thing. Okay. All right, that's got us a few examples there. I hope that gets you going. I will see you all in class.